the example I want to do here is one that we've already seen, which is the two trains, x versus t. One train is traveling at constant velocity, and one train is slowing down the whole time. And that wasn't the way the problem was stated, but it just gave the graphs of two trains and asked the question about when do they have the same velocity. And the answer is when their slopes are the same, because it's x versus t. I want to do this problem numerically. So I've defined my two trains. Whoops, train 2. Train 1 is traveling at an initial velocity of 100 meters per second and slowing at 1 meter per second squared. All right, that's a little fast, but trains can go that fast. Train 2 is traveling at a constant 50 meters per second. Let's say that they start at, TA, and they finish at time TB. TA might just be at t equals 0. They start in Lynchburg and they go to New Orleans, whatever. And I'm not saying that they get to New Orleans by TB, but that they're just traveling along two parallel tracks. And I want to know, when do the two trains meet? When do the two trains meet? So if you look at the graph, when are the two trains at the same place? I'm going to go back and look at the graph. Look at the graph. The two trains are at the same place when their x positions are the same. So they're at the same place at TA and at TB, right? And let's just say TA is t equals 0. So they're at the same place when they start, and they're at the same place sometime later TB. So let's say TA is equal to 0, and so we want to know what is TB. So how are we going to figure this out? How are we going to figure out when they meet? This is the first problem that we've done where we have two objects traveling at different accelerations. In order to answer that question, we need to write down the kinematic equations for each object separately. So I need to write down the position, the kinematic equations. In this case, we're actually only going to care about the position function, the quote-unquote first kinematic equation, but we got to write down the kinematic equations for each. So for train 1, I've written down the three kinematic equations, and I've written down the variables, which we didn't draw a picture, but from the graph and the description, delta x is an unknown. We don't know how far they've gone. A, remember, it was 1 meter per second squared and was slowing. It's moving in the plus x direction. That was, the graph told us that. The graph showed us it was moving in the plus x direction. So the acceleration, since it's slowing, must be minus 1 meter per second squared. Initial velocity is positive 100 meters per second. It's moving in the plus x direction. Final velocity is unknown. It hasn't stopped. The picture may look like it stopped. We don't assume that it stopped. And the time that it takes is unknown. That's what we're looking at. When are train 1 and train 2 at the same place? T is unknown. So T is what we want to find. I'm going to go ahead and do the same thing for train 2. Let's even do it on the same piece of paper, because train 2 is traveling at constant velocity, so that's a lot easier. For train 2, we have the same three kinematic equations, and the variables for train 2, we don't know how far it's gone. The acceleration is 0. The initial velocity is 50 meters per second in the positive direction. The final velocity, because it's constant, is 50 meters per second in the positive direction. And the time is unknown. And we want to find the time. Now, one thing that we need to be careful of here is we're talking about two separate trains and two separate sets of variables and constants. So we really need to put subscripts on all of these variables and constants. So for example, this is train 2, so I'm looking at the right hand side, delta x sub 2, acceleration for train 2, initial velocity for train 2, velocity for train 2, and t for train 2. And then we go back to the left hand side and we say that these variables, delta x1, a1, v01, v1, t1, they're different because it's a different train. And then we got to ask which are the same and which are different from each other. For example, when we're asking when are train 1 and train 2 at the same place, what does the same place mean about the variables? How does that, what does that imply about the variables? If they're at the same place, can you compare delta x1 to delta x2? If they're at the same place, then delta x1 must equal delta x2. Okay. And at the same, and being in the same place, we imply when at the same time, therefore T1 equals T2. So we're talking about the same position and same time. Different accelerations and velocities, but same position, same time. Okay, so now I'm going to take the kinematic equation for delta x, because that's what's interesting, is when they're the same place at the same time. So I'm just going to take the first kinematic equation, write it for train 1, and write it for train 2, and set them equal to each other. So I got to go to a new page, but I'm going to be using this kinematic equation and the defined variables and constants below. So here I've written down that first kinematic equation, delta x as a function of t, for train 1 and for train 2. Then I can set them equal to each other and say their times also must be the same. So for t1 equals t2. So we can just change, drop the subscripts from the times and just say the times are all the same, really. We could just say t1 equals t2 equals t. So set them equal to each other, and I get minus 1/2 meters per second squared times t squared plus 100 meters per second times t equals 50 meters per second times t. So it all simplifies, and we just solve for t. Here we solve for t. We can divide out a t on both sides, divide out a t on the right, divide out a t on the left, and say, ooh, that means that t equals 0, or we can divide it out. And so therefore we get this equation. You can do the algebra. I'm going to skip on ahead and say, therefore, t is equal to 100 seconds. Units work out, signs work out, is positive 100 seconds, t is 100 seconds. So the trains pass each other at t equals 0, that we already knew, we already defined that, and then again at t equals 100 seconds. So where do they meet? Let's ask the question, where do they meet? So that's the second part. Part A was when do they meet, part B is where do they meet. Well, in order to figure out where they meet, all we have to do is go ahead and plug this time back into either position equation. And if you plug it into either position equation, in other words, we're going to take this t equals 100 seconds, and we're just going to plug it in everywhere or anywhere we see a time, and ask, if we plug in t equals 100 seconds, what do we get for delta x1 and delta x2? And in both cases, we should get the same thing, and we will get plus 5,000 meters. So I just wrote out the solution here, that they meet at 5,000 meters after 100 seconds. That's the second time they meet, because the first time they were together was at t equals 0 and x equals 0. Okay, so that's how to deal with two bodies. You just write down your two parallel sets of kinematic equations and variables, and then you have to compare, if we're asking something about the relationship between the two, you have to compare the variables for the first body to the variables of the second body. Maybe we're asking what happens at a given time, so time is the same. What happens in a given place, so place is the same, etc. If I wanted to, I could ask another question, which was the original question, which is basically, where do they have the same velocity? Or I mean, at what time do they have the same velocity? That was the original question, right? The clicker question that when we did this. At what time do they have the same velocity? In order to answer that question, what do you think you'd do? There's a couple things you could do. You could look at the graphs and you could understand that given the constant acceleration motion that it's got to be halfway between, so it should be 50 seconds. But we can prove that using the kinematic equations, right? So you just go to the second kinematic equation. V equals V0 plus AT. You write it down for one train, you write it down for the other train, and you solve for T. What I would like to do is leave that as an exercise for you. You should show that the time at which they have the same velocity is 50 seconds. And figure out, don't in your head do it, write it out on paper, figure out how to show that they have the same velocity at t equals, I'm giving you the answer, at t equals 50 seconds.